Hi, welcome back to my channel. Today's video is going to be an introduction to signed integers and subtraction. So it's necessary for me to talk about signed integers at this point because there's a very likely chance we'll go below zero in the result of our calculations. If we're working with a single byte, we can record the sign of that number at the expense of losing the most significant bit. So as you can see in this example here, I've actually sectioned off the MSB here, and by following this example we can see that if the signed bit is at 0, then we have a positive number. So we're going to store 127 into there. If we decide to use this signed bit, we write a 1 to the MSB, then we have to make sure we remember that we're dealing with a negative number. If we treat this number differently and fill all of the ones, then we come out with -1. But we must treat the number differently to a positive integer because otherwise we'd be looking at 255, which is not what we're looking for here. So the way that this works is the Commodore 64 uses something called 2's complement, and how this works is if you want to know what the negative version of a number is, there's a little operation you have to perform. Let's say we have the number +3 and we want to find out how to express -3. The first thing to do would be to set the sign bit and also invert every single bit in that number. And then you add 1 to the result. So this is why we have a very strange looking number that doesn't make any particular sense when you first start looking at these things. But here, this is how we go from +3 to -3. We can see the sign bit is set, so we know it's a minus number, or we're going to treat it like it's a minus number. And then we have the result of flipping each bit and adding 1. If we wanted to express -1, we'd start with this number, we flip all the bits, and then we add 1. And this is why -1 is a full set of 1s. If we had the number 16, again we invert all the bits and we add 1. And what actually happens here is because we've added 1, all these bits would carry over. You'd end up with this strange looking number, but this is -16. And I've also put some more examples in below, and you can roughly see how that would work. Okay, so as always, I've written a little program to demonstrate this. This program will take the number 9 and subtract the number 12 from it, which should give us -3. And depending on the outcome of the subtraction, if we decide that this was a positive result, we're going to store it in an area that we earmark to say the number here is positive. And if the number was negative, then we'll store it in the negative area. This is probably not the most efficient use of memory, but it should serve enough to demonstrate the concept of how this works. So we define our two numbers here. We have 2 bytes for the result. The actual subtraction takes place here, and you can see we have a set carry flag. So before we undertake the subtraction, we're going to set that carry flag, which is the opposite of what we did with the addition. We load number 1, which is 9, into the accumulator, and then we subtract with carry the number 12. And then the only logic that this really does, we've got a BMI, which is branch if minus. This will read the negative flag and will branch if that negative flag is set. Don't get confused with BNE, because that's branch if not equal. You can easily get the two of these mixed up. The BMI command branches the code if the minus flag was set. If that minus flag is not set, so we have a positive result, we're going to store the result in positive result because it's a positive number, and we're going to store 0 in negative result. And the opposite takes place. If that BMI flag was set, we're going to store the result of our calculation in a byte called negative result, and we're going to store 0 in positive result. Hello again, we're back in our old friend retro debugger. We're going to run the very simple program that I just explained to you in the code, and I've zoomed the what I call the status register, I suppose, to the highest amount. We're going to keep an eye on the negative flag there, because the result of this negative flag when we subtract these two numbers is going to be what branches our code. So let's see what happens. We have taken 9 and we've subtracted 12 from it, and we can see that the result of this is driven the negative flag to 1. So the result of our branch, which is the BMI command here, should jump down to 822, which is this one. It's going to store the negative number in the negative result that we've arranged for. It's going to store, hopefully, a negative number. And there we go. That's registering -3. You'll notice that I've actually set retro debugger to be signed decimal 8 bits. So we know we're reading in a signed number. If I change this to binary, it looks like just any other normal number, doesn't it? If I change this to binary, you can see what it's stored in there. And that is the end of the program. So having talked about a single sign byte, I probably should mention how we would deal with a larger number than that. I'm going to refrain from writing code for this, just because I think it's quite a complex job, but this is what we're looking for. If you were to want to express a very large number, then what you would have to do is the same as an unsigned number. You would have to define an extra byte or more bytes in order to store that number. The difference here being that when you do this, your most significant byte will be the signed one and your least significant bytes will be unsigned. So the way this works is, if we just imagine for a moment that our lowest byte contains nothing, it can be a little bit difficult to get your head around. It certainly was for me. We are adding every single number and then we are going to minus that number. So if we've got a full set of ones, we end up with 256, which is a bit weird. But what it's effectively doing is we're saying we're going to add every single number. First example, we haven't stored any number into the low byte at all. But you can see here that if I fill all the ones, we get minus 256. And that increases in a similar manner to how we define a unsigned or a positive number. So the way to think about it is like this. We start off with this number. If we're going to add a positive number to this, then that number is going to get higher. It's going to tend towards 0 instead of getting further away from it. We're going to start with a negative number and we are going to add positive numbers to it. So it does look a bit weird that minus 256 is all ones, but we're going to start with this number, we're going to add that to it, add all these numbers, and we should eventually end up with the lowest number we can express in that byte. Look at this number, which is minus 32,768. We're not going to add any numbers to that. Because we're not adding any numbers to it, we've got a very large negative number. So you can kind of see how the high byte works if we're going to do this as a 16-bit. The interesting thing is that when you have got 2 bytes, then the first byte is treated as a unsigned number. You're going back to using 8 bits again. So in this case, well, this MSB is used for the sign. These have all gone back to 8-bit numbers again. If we want to express minus 1, we need the lowest number we can express on the high byte, which is minus 256, which fills all of that with ones, and we need the highest number. What happens here, we start off with minus 256. We add positive 255 to it, which brings us to minus 1. If we want minus 2, then we're going to take our 256 and we're going to add 254 to it to get minus 2. And this is how this all works. You can see there's a pattern emerging here. Where it gets complicated, if you want to store a number that's larger than 128, that would be this number. Because we're taking minus 256, we add 128 to it. If we want 129, it kind of wraps around. You can see what's going on there. What we're effectively saying is, take that minus 256, and now we're going to add 127 to it. So you've kind of got to switch your brain between signed and unsigned to make this work. But I'm not going to attempt to write code to do this because I feel as though it's probably getting a bit far away from what I want to do. But this is just to explain how the numbering system works, and that much like with the addition that I showed in the previous example, you have to manage this all by yourself. So this is just to outline the challenge that faces you if you want to store large numbers, very large numbers, or even larger. You can certainly go larger than the numbers that are on this screen, but you've got to chain your bytes together. Your code would have to manage all of that. I think that's a little bit beyond the scope of what I want to talk about on my video. If there's anybody out there that's considering doing this, then good luck to you. But that's just a brief primer on signed integers. And that's all for now. Thank you very much.